Hey everybody, it's Mr. Roy. Here's a quick lesson, well fairly quick, on the applications of trigonometry. We're going to take what we learned from trigonometry and we're going to apply this to some problems that have a little more meat to them than the ones we've been looking at before, where we're just solving for triangles with nothing in them. We're also going to learn some new vocabulary in this lesson. So let's jump in. Here we go. So when we're using trigonometry and we're solving problems, we're often going to need to do some interpreting of the things we're reading in order to understand what things are actually going to look like. There are mainly two situations we're going to look like. So I'm going to introduce you to two new terms. And let me get my highlighter out here so I can highlight all over them. Here's my first one. Angle of elevation is our first term. What this means is if you look horizontally and then you go up from there to a certain angle, that's called my angle of elevation. So from the horizontal up, this could be from the ground up, it could be horizontally from your eye line where you're looking up, but it's always going to be from the horizontal up. The other one is called angle of depression, and that is from the horizontal line down. So this could be looking from, you've got the water on a lake, and then an angle downwards from there. It could be an aircraft that is descending below the horizontal line. Lots of different things like that. Or it could be someone standing on a cliff looking downwards. That's called our angle of depression. Okay, so those two terms we're going to see in a number of problems going forward. Okay, let's go back to a regular pen here. So we're just going to do some math. Okay, so here's the other thing. We can also use our patterns, angle of elevation and depression. They're related by the Z pattern, right? So they're going to be equal to one another. So we might be given an angle of depression and we have to use an angle of elevation to solve a problem. In that case, they would be equal using that Z pattern, and one would give us the other. Okay? So we're going to use those angle things we've learned to apply here. Here's our first problem we're going to get into. And this is similar to the shadow ones we did with similar triangles. The angle of elevation of the sun is 23 degrees. So that means from the ground up, it's going to make an angle of 23 degrees. We've got a building that's 76 meters tall. That's a tall building. How long is its shadow going to be? Okay, so let's draw some angles here, or some lines on here. My first line is going to be the line that the sun makes with my building. So that's going to extend to here, and that's going to be a line where my shadow ends on the ground, okay? And this is my horizontal line to my building. And then this line is going to be the height of my building right here. So here's my right angle triangle. I can assume it's right angle because that's how we build buildings, frankly. We build them straight up and down. Okay, so let's do a little bit of labeling here. Let me find where I put my smartboard pen. Okay, I got it. Here we go. So let's label this. First things first, the building's 76 meters tall, so let's put that on there. Also, the thing I want to know, how long is the shadow going to be? Let's just call that x. That's the thing I want to find out. And my angle of elevation of the sun is right here. It's 23 degrees. So we're starting at the horizontal and going up, and that's the line that would extend all the way out to the sun that makes that shadow on the ground. Okay, so first thing I'm going to need to do is decide which ratio I'm going to use. So I'm going to write up here my good old SOHCAHTOA, and that's going to remind me what these different ratios represent. Now I want to label the sides of my triangle. So I've got my angle of 23 degrees, that's where I'm looking from. This is going to be the opposite side the building is, and the adjacent side is the ground where the shadow is. And the hypotenuse, I don't know it and I don't care to know it, so I'm not going to include that. That's not what I'm interested in. So I go, okay, opposite and adjacent. Opposite and adjacent. Oh, that's tangent ratio. Uses opposite and adjacent. So we're going to say, okay, tangent ratio, so tangent of 23 degrees is the opposite side. That's going to be 76 meters. Over the adjacent side, that's x, our unknown. Let's pretend this is over 1. Let's do our cross multiply game. 1 times 76 is 76. X times tan of 23 is x tan 23 degrees. Now I'm going to divide both sides by tan of 23 to move it over to the other side. So x will be by itself, and we're going to have 76 over tan of 23. I will warn you, the most common mistake I see in trigonometry is students are trying to solve this and they end up moving the tan of 23 to the other side and they just multiply it by 76. So they go 76 times tan of 23. That wouldn't be correct. We need to divide both sides by tan of 23. So it's going to end up on the bottom over here. Let's plug that into our calculators. 76 divided by tan of 23 degrees, which is going to be its own number, right? That's not two things. Tan of 23 degrees is one number. It's one ratio. And if we do that, we're going to end up with 179 meters. So I'm just going to put the number like this, but this is a word problem, so I need to write myself a therefore statement. So I'm going to do a little therefore, and I'll say the shadow is 179 meters long. Okay, so that's my first one using an angle of elevation. Let's keep on rolling, and let's move on to an angle hill incline problem. So here's our next one. A hill rises 50 meters for every 1,000 meters of run. So it's not a super steep hill, but I want to know what the slope or angle, also called the inclination of the hill is. Okay, so this has a lot to do with road engineering. So civil engineering, which is actually a really important job. The city of Thunder Bay employs a lot of people who are civil engineers, and what they do is, one of the things they would do is the mathematics and engineering related to designing and using roads. Okay, so let's actually use our little picture of Jack and Jill going up the hill here. And let's do a little diagram. So our hill looks like kind of like that. That's exaggerated. Of course, it's not that steep. But I'm going to use this just to make things easier to see. And I'm going to say, okay, that's my 1,000 meters of run, and this is my rise of 50 meters. Of course, this is going to make a nice red angle triangle. Let's label what we know about those. So we'll say, all right, this is 1,000 meters, and this is 50-meter rise. And what we want to know is this angle, so I'm actually going to use the theta symbol. Ooh, that's not showing up very well against the blue. But I'm going to use the theta symbol for my angle because usually that's my default symbol for an angle if I don't have another one. You could use X or Y, that would be totally fine, but I like theta because it tells everyone right away that it's definitely an angle because that's always what it's used for. Okay, let's do the old SOHCAHTOA dance. SOHCAHTOA. Let's see. I'm going to need to label the sides of my triangle to know which ones I want to look at. So if my angle is there, my opposite side is over here. That's the 50. The adjacent side is the one that's touching my angle. And the hypotenuse, I don't know and I don't care about my hypotenuse. So I'm not even going to label it. So make sure not to use that. Looks like I'm dealing with tangent again. You could also say, because hypotenuse is in sine and cosine ratios, that automatically rules them out. So let's do the math here. I'm going to say I'm going to use a tangent ratio. Tangent of some angle I haven't figured out yet is the opposite side over the adjacent side. The opposite side is 50. The adjacent side is 1,000. And now let's do my inverse to find my angle. So I'm going to look on my calculator for that second function button. I'm going to hit that, and then I'm going to hit my tangent button, and I should get my tangent inverse, which is basically a way of undoing the ratio to get the associated angle. Now I could go 50 divided by 1,000 and just get that decimal or that number and plug it in here. But instead, to make things easier and quicker and more exact, I'm just going to, in my calculator, do 50 divided by 1,000. Okay, and so I'm going to end up with an angle of, well, it's a really tiny angle. I'm going to go to a couple of decimal places here because it's such a small angle, 2.86 degrees. It's really tiny. And then I'm going to put a therefore statement. So we'll say, therefore, the hill has a slope of 2.86 degrees. Okay, so that's my slope right in here for my hill. Okay, so we've used this so far to find a side of a triangle, to find an angle, but of course they have context. Let's move on to an angle of depression question. So here we go. We got a plane approaching a runway at an elevation of 2,500 feet. The plane is descending at an angle of 13 degrees. So that tells me we're looking at an angle of depression. So let's work on my diagram here a little bit. You might hear my dog barking in the background, so you get to enjoy that too while I go. Okay, oops, that's not what I want. I want a nice straight line here. Let me get a dotted line. Okay, pardon me folks, I'm going to pause the video while I go tell my dog to stop barking. Alright, I'm back. Can't have the 7-year-old woken up after all. Okay, so there's my horizontal line, right? And my plane is going to be actually going at an angle lower than that. So my plane is actually going to be traveling like this, right? Kind of like that. And that's the direction that it's going. So if I want to use my label here to put in my angle, I'm going to say this is my 13-degree angle right here. Okay, well let's add a little bit more to our diagram. I know that my plane is going to be a certain distance from the airport, and I happen to know how high up in the air it is. And of course this is going to make a nice little right angle triangle for me too. Alright, let's finish labeling our diagram here. So this is 2,500, we're working in feet, 2,500 feet. And we say, how far is it horizontally? Well, let's just call that distance x. That's what we don't know. Now, right now, we know one side of the triangle. We don't know any of the other sides, and we don't know any of the angles except the 90-degree angle. So right now, we're stuck. But I can use my z pattern here, right? This angle here of 13 degrees by z pattern is actually going to equal this angle right here of 13 degrees. Now that I know an angle in my triangle, and at least one side, I can find all the other information I need. So I can figure out what that other side is. So here we go. What ratio am I going to use? Let's do our old SOHCAHTOA. I'm going to label my triangle. Looking from that 13-degree angle, x is my adjacent side, and 2,500 is my opposite side. So that means I'm going to use my tangent ratio, opposite and adjacent. You might be getting tired of using tangent ratio, but in real world problems, the opposite and adjacent sides are overwhelmingly the ones we actually end up using. So tangent ratio shows up quite a bit in these sort of situations. So I'll say tangent of 13 degrees is going to be my opposite side over my adjacent side. So my opposite side is 2,500. My adjacent side is x, my unknown. Let's put this over 1 and do our cross multiply game. We're going to end up with x times tan of 13 degrees is equal to 1 times 2,500. How do we get x by itself? Well, we divide both sides by tan of 13. So let's do that. Divide both sides by tan of 13. I'm going to end up with 2,500 over tan of 13 degrees. Plug that in my calculator. 2,500 divided by tan of 13, whatever that happens to be, I'm going to end up with 10,828.7 feet. So let's keep that to one decimal place, and I'll put my box around my final answer there, and I'll write my little therefore statement. I'll say therefore the plane is horizontally 10,828.7. I mean, that's stretching it to know that we're that accurate, right? So 10,800 is probably a more accurate number, but a more realistic number to say is horizontally that for feet from the airport. Okay. There's two more I want to do. So here's our next one. We've got a fishing problem. This one's actually pretty tricky. So the tip of a fishing rod is 1 meter above the water. So let's just start with that. The tip of the fishing rod is 1 meter above the water. I'm going to put a line from the tip of the fishing rod down to the water. That's 1 meter. Let's label it 1 meter. Okay, so far so good. The fish finder in the boat has identified fish at a depth of 45 meters. So I'm not going to be able to draw this to scale, right? Because I'm going to run out of room. So I'm just going to have to kind of draw it and do my best. So it's going to go like this, and this below the water space is going to be another 45 meters. 45 meters. That means the whole thing, that whole line from the tip of the fishing rod down to the fish is going to be 46 meters, that whole distance, okay, when I add the 45 plus the 1. And now we say how much line is needed to catch the fish if the line is at an angle of 67 degrees to the surface. So here's the surface, right, and if the line is going in like that, we're talking that angle right there is 67 degrees. So let's actually put that on our original diagram. So I'm going to get another line here, and I'm going to draw it down like this to here. And then I'm going to finish off my diagram by finishing off the triangle here. And we'll, of course, indicate that that is a right-angled triangle. There. So here's the thing we can figure out. Let's do a little more labeling here. I know that this angle right in here is 67 degrees. Now I can actually use my F pattern. My F pattern will tell me that this angle is also 67 degrees. So my F pattern tells me that's also 67. Okay, so if that angle is 67, and I know the opposite side is 46 meters, I can use trigonometry to solve this for me. Let's do my old SOHCAHTOA. From the angle I'm looking at, I know that this is my opposite side over here. My adjacent side I don't really care about. My hypotenuse I do care about. It's actually what I want to calculate. It's the length of line, right? So I'm going to put in x on this side because that's what I want to figure out, is the hypotenuse of that triangle. How much line is needed to catch this fish that's right here. It's not a very good fish, but it'll have to do. Okay, so opposite and hypotenuse. What do I want for opposite and hypotenuse? I want sine. Sine uses opposite and hypotenuse. So I'll write out my ratio. I'll say sine, and I'll write out my angle, 67 degrees. Now I need to write my opposite side, 46, because it's the whole side of the triangle. 46, 45 plus 1, over hypotenuse, which I don't know, which is x. Okay, let's solve. Let's say that's over 1. 1 times 46 is 46. X times sine of 67 is x times sine 67 degrees. Let's divide both sides by sine of 67, so I'm just left with x on the right. On the left, I've got 46 over sine of 67 degrees. Now it's some calculator work. Let's plug it into our calculator. 46 divided by sine of 67 degrees. I'm going to go to one decimal place. It's going to be 50.0 meters of line. Let's put our little therefore statement over here so I don't have to take the question off the screen. And I'm going to say, therefore, we will need 50.0 meters of line to catch this fish. Okay, let's go to our last one here. This one looks tricky. It says determine the area of the triangle. All right, well, let's remind ourselves our formula for the area of a triangle. Area of a triangle is base times height over 2, or 1/2 base times height, right? So which of those do I know? I know the base, it's 42. So that's good, but I don't know the height. Now remember, the height has to come from the peak straight down and hit the base at a 90-degree angle like that. And it's going to be 90 degrees on both sides, but I'll just draw it on one side because we know it's going to be 90 on the other as well. Now you might be tempted to split this into two and say 1/2 is 21 meters and the other half is 21 meters, but they're not equal, so you can't do that. We don't know how long each of those sides are. So let's call this h for the height of our triangle. We do, though, have a right angle triangle. Let's use our trigonometry. Now we say, okay, 42, that's the whole thing. That's not going to help us to know this side of the triangle, but we do know the hypotenuse right here. It's 16 meters. We do know this angle right here, that's 62 degrees. That's enough information to find any other side of the triangle, like the h, the height measurement. So let's do that. Let's label this triangle here. I'm going to say, okay, if I'm looking from 62 degrees, this is my opposite side, and this is my hypotenuse. I don't care about my adjacent, and I don't know it, so it's no good to me. If I write out the good old SOHCAHTOA, the opposite and the hypotenuse is sine ratio. So I'm going to use the sine ratio to solve. So I'm going to go sine of 62 degrees is going to be my opposite over my hypotenuse. Opposite is h, our unknown. The hypotenuse is 16. Let's pretend this is over 1. Well, it can be over 1. It is over 1. 1 times h is h. 16 times sine of 62 is 16 times sine 62. Gonna plug that into my calculator. See what I get. I'm going to end up with 14.127 if I take it to a few decimal places there. And because this is not my final answer, I don't want to round off too much yet. Now let's do my area calculation. So let's go back to my area formula. So area is base times height divided by 2. So my base is 42. My height I've calculated is 14.127. And I'm going to divide that by 2. That's going to work out to 296.67 meters squared. Let's round off to one decimal place. So 296.7 meters squared. Now there actually is another way to do this. So you can use the formula for a triangle, you can use trigonometry to find the measurements you need, but there actually is a bit of a shortcut. And here it is. Okay, it's going to basically do what we just did. It's going to take the formula for area, but instead of using the height, it's going to substitute in this side, 16, times the sine of the angle. So have a look. Here it is. This is our shortcut. In general, the area of a triangle is given by area equals 1/2 times AC sine B, where sides A and C contain the angle B. So in this case, side A is 16. Side C is 42. And we do the sine of 62, which is in between. And then multiply it by half or divide by 2. So this is a little formula that will do that for us. Let's try that out. Okay, let's actually try that formula. I'm going to change my view here. Zoom out just a little bit so we can see more of the page. So we're going to use this formula. So area is going to be equal to 1/2 times 16, that's one of the sides, times 42, that's the other side, times the sine of the angle that's in between those two sides. And when I calculate this, it's going to work out to the same thing, 296.7 meters squared. And let's do a little therefore statement. Therefore, the area is 296.7 meters squared. Okay, so you can do it from scratch, or if you want, you can use this shortcut if you know two sides and the angle in between them. That's a nice little shortcut for finding the area of a triangle. Okay, now you've got some stuff to work on and a little bit of practice. I hope this goes well, and I'll be happy to chat with you about some of these problems. The trickiest part usually is drawing your triangle, interpreting the information you're drawing your triangle. So always start by making a nice, clear drawing. Hope to see you soon, folks. Bye for now.